So last time we met, we saw that the Bohr model didn't explain everything there is to explain about the atom, bonding, electrons, all these good things. So we move on to this quantum mechanical model of the atom, and we have this thing called orbitals instead of just those planetary rings. How is an orbital different? Well, they represent a probability of finding an electron. It's like a definition on your take-home quiz today. An orbital is a region of 3D space where there's a high probability of finding an electron. And they get mapped out and they kind of have shapes. So quantum mechanics revolutionized physics and chemistry because in the quantum mechanical model, electrons do not behave like flying particles through space. We cannot in general describe their exact path. So an orbital is a probability map that shows where an electron is likely to be and found when the atom is probed. It does not represent the exact path an electron takes as it travels through space. We just kind of imagine the shape where there's a high probability of finding an electron. So here's a baseball analogy. So we're going to pretend that a baseball might be kind of like an electron. Imagine a baseball thrown from the pitcher's mound to the catcher's home plate. The baseball's path can easily be traced, and we see where it goes. Can't do that with electrons, but we're going to just use this as an analogy. In the quantum mechanical world of the electron, the catcher would not know exactly where the electron would cross the plate for any given throw. He'd have no way of putting his mitt in the right spot to catch it. However, this is the catcher. I'd be like, please don't hit me. However, the catcher, he gets some muscle memory. He sees where these all come most of the time. And he could observe a reproducible statistical pattern where the electron crosses the plate. So 70% of the throws are going to be here, right? Except for that one that hits the batter by accident. And 40% of them might be in here, 20% of them in there. My only problem is the percentage isn't adding up to 100. Seems like if you make this thing big enough, so like right here, 20% are only in that area there. So here is a statistical probability map of where the ball's going to be. So you can close your eyes and not look at any ball, and there's a 70% chance it's going to be in this circle, 40% chance in this circle, 20% that it's in that circle for any given pitch. So that is what a probability map is. In the quantum mechanical model, a number and a letter specify an orbital or orbitals. The lowest energy orbital in the quantum mechanical number is called the 1s orbital. And eventually on your periodic table, we'll write something like 1s going across from hydrogen to helium. The number is called the principal quantum number, n, and specifies the shell of the orbital. A single electron of an undisturbed hydrogen atom at room temperature is in the 1s orbital. This is called the ground state, or lowest energy state of the hydrogen atom. Then we put that gas tube in that lamp, and of course it goes up into those other states. The absorption of energy by a hydrogen atom can cause the electron to jump or make a transition from the 1s orbital to a higher energy orbital. When the electron is in a higher energy orbital, the hydrogen atom is said to be in an excited state. It goes back to a less excited state. That's when you get the photon of light emitted. All the atoms of each element have one ground state and many excited states. The higher the principal quantum number, the higher the energy of the orbital. The possible principal quantum numbers are 1, 2, 3, 4, 5. We can go up to 7. We can imagine going higher, but that's it. Since the 1s orbital has the lowest possible principal quantum number, it is in the lowest energy shell and has the lowest possible energy. The letter indicates the subshell of the orbital and specifies its shape. So we have S, P, D, and F. So I'm told these letters, they seem completely random, but S at one time stood for sharp, principal, diffuse, and fine in describing certain spectral lines. That's just a historical for your information thing there. Orbitals with the S subshell have a spherical shape. And so we represent these probabilities of finding an electron with these geometric shapes that encompass most of the volume where an electron is likely to be found. The 1s orbital can be represented as a sphere that encompasses the volume in which the electron is found 90% of the time. If we superimpose the dot representation of the 1s orbital on the shape representation, we can see that most of the dots are within the sphere, meaning that the electron is most likely to be found within the sphere when it's in the 1s orbital. So there's actually some mathematics and equations that produce these. So here's a bunch of dots representing where we could find an electron in a 1s orbital. Here's the shape representing the 1s orbital. And here's both representations superimposed. So it's kind of like the catcher's mitt. Sometimes electrons are outside of the sphere, but 90% of them are in that sphere. All right, the number of subshells in a given principal shell is equal to the value of n. So when n is 1, we're filling up the 1s. And then if you look up at the periodic table, we just see 2 elements. I can put 2 electrons in there, and that will accommodate hydrogen with its 1 electron, and then helium with its 1 electron. Then we drop to the next shell, n equals 2, and we have 2 subshells. We have an S and a P. The third shell, we have 3 subshells, an S, a P, and a D. When we get to shell number 4, we have 4 subshells, an S, a P, a D, and a F. So what's the difference between the 2s and the 1s? The 2s is larger in size. So the 3s is even larger and the 4s is even larger. Then we move on to this 2p orbitals. So there's a set of 3, and they kind of have a dumbbell shape. And in 3D space, they are along each of the 3 axes that define 3D space, like one along the X, one along the Y, and one along the Z. And so there's this rule that says I can put 2 electrons in an orbital. So that first shell, we had the S orbital, and if you can put 2 electrons in there, notice that accommodates 2 elements. So then when we get to the next level, if I can put 2 electrons in here, 2 more in here, 2 more in there, that's 6, right? So here on the periodic table, how many columns do we find? Find 6 columns. We'll see how that works in a second. The next principal shell, n equals 3, contains 3 subshells. We have an S, a P, and a D. The S and P subshells contain the 3s and 3p orbitals, similar in shape to the 2s and the 2p, but just larger. And we say higher in energy. The D subshell contains 5 orbitals. If I can put 2 electrons in each orbital, how many electrons does that accommodate? 2 times 5 is what? And how many columns do we see over here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I tell students, you always have a periodic table in front of you, maybe off to the side. So that's going to help you out. So here's what the 3D orbitals look like. We kind of have this clover leaf of dumbbells in one axis, another clover leaf in the other axis, another clover leaf in this axis, and then this one here. And this is the chemist's favorite. It's the hourglass with the donut ring. So nature just kind of like mathematically with the Schrodinger equation and quantum mechanical math just prints these out. So why is this shape? That's just what nature and math gives us. Why is this shape? It's just what nature and math gives us. All right, well, maybe that seems kind of strange. Why are orbitals better? The quantum mechanical model predicts the bright line spectrum of hydrogen as well as the Bohr model does. The quantum mechanical model can predict the bright line spectra of other elements. The Bohr model cannot predict spectra for atoms with more than 1 electron. The Bohr model was replaced with a more sophisticated model called the quantum mechanical or wave mechanical model. The Bohr model is still important because it provides a logical foundation for the quantum mechanical model and reveals historical development of scientific understanding. So if we talk about the electronic structure of the atom, that means where are the electrons? What are they doing there? So we have this thing called electron configuration, and it's just kind of like an address system, tells us where all the electrons are. An electron configuration shows the occupation of orbitals by electrons for a particular atom. So hydrogen with its 1 electron, where's it going to be in its ground state? We write this thing, principal quantum number 1, and then S, because there's only 1 orbital in the first shell, the S. And the superscripted 1 means there's 1 electron in there. Gives us the number of electrons. So we kind of have orbital, electron, and quantum number n. So another way to represent this information is with an orbital diagram, which uses little square boxes to give similar information, but shows the electrons as arrows in a box representing this thing electrons possess, which is called spin. So here's an orbital diagram for a ground state hydrogen atom. We have this 1s that tells us what this box is, and here's this half arrow pointed up, telling us what that electron is doing perhaps. Box represents a 1s orbital, and the arrow with the box represents the electron in the 1s orbital with its spin up. All right, now we're going to move on to putting 2 electrons in an orbital. The direction of the arrow pointing up or down represents electron spin, a fundamental property of electrons. So the Pauli exclusion principle states that orbitals may hold no more than 2 electrons with opposing spin. So when you put electrons into orbitals, you can only put 2 electrons into an orbital, and they're going to have opposite spin. Might have to do with magnetic moments and how you can get them to fit in there. In a multi-electron atoms, the subshells with a principal shell do not have the same energy because of electron interactions. And it turns out electrons shield other electrons from the positive charge of the nucleus. Different subshells within the same principal shell have different energies. The 4s subshell is lower in energy than the 3d subshell, even though its principal quantum number is higher. So I guess I can do this now. There we're filling up the 1s. And this really is delineating this line here. Here we're filling up the 2s. Here we're filling up the 2p, 3p, 4p, 3d, 4d, 5d, 6d. So we fill up the 4s before we fill up the 3d, and then we fill up the 4p. So if we can find an element like phosphorus, we can look up at the periodic table and see atomic number 15. That means I have 15 electrons. Where are all those electrons up at? Well, that's filling up the first shell. Then I come down and I have the second shell, which has 2 we might call subshells. When I blaze through those 2 boxes, I fill them up. 1, 2, 3, 4, 5, 6. Because you got those 3 orbitals, you can put 2 electrons in each one of those. All right, now I'm down to this 3s, and I put 2 electrons in there. And now I'm gotten to the 3p, and I count over 1, 2, 3. So here's the electron configuration for phosphorus. And this tells me quite a bit, perhaps. Gives me the number of valence electrons. Looks like 5. Gives me the core electrons. Looks like I got 10. What do 10 and 5 sum up to? 15. So now I know everything there is to know about phosphorus's electrons. And this is how you write an electron configuration. So I handed out the periodic table so you could just label it. So even though this subshell has these subshells, the 2s has a 2p and the 2s, this gets pushed up higher in energy due to things we don't go over in intro chem. We go over it quite a bit in general chem. And this thing gets pushed up, and it kind of gets worse as we go. But a couple of slides ago, it said we fill up the 4s before we start filling in the 3d. Otherwise, we fill from low energy. Well, we always fill from low energy to higher energy. So we're always going to fill up like this. But here, we don't get to the 4p till after we've filled up the 3d. Then we start filling up the 4p. See, here's the 3d, and then here's the 4p. Oh man, after we did phosphorus, why should we do helium and carbon and nitrogen? All right, so you find helium, second element on the periodic table. It has 2 electrons. Where are you going to put them? You're going to put them in a 1s. Let's go down to lithium. You look over there and you see atomic number 3. You got 3 electrons blaze through the first row on the periodic table, go down into the second row, first element in. So there is where they're all at. So how many valence electrons does lithium have? Valence electron. Probably need the slide that says what a valence electron is. A valence electron is electron in the highest energy level. What's the highest energy level here? Yeah, the 2s. And what do you see in there? 1. And we'll see here shortly that every element in there has 1 valence electron, and I tried to tell you that from day 1 when I said metals give up electrons. So what's the charge on a lithium cation? It is positive. What's the magnitude? 1. Yeah. So the electronic structure, you already know how it dictates a little bit of chemistry, because things I try and drill into people's head from day 1. All right, let's go to carbon. 6 electrons. Where are they all at? There's the first row of the periodic table filling up. Drop down. This corresponds to the lithium and beryllium, and carbon's the second one in. And something interesting is going on. I put an arrow like that to represent 1 electron, then another one. Don't really need this picture to write this down. The 2 p electrons occupy the p orbitals of equal energy singly rather than pairing. So I don't write one paired until I fill this thing all the way up. So this is an important thing. It's so important we named it after the fellow that came up with it. Hund's rule. When filling orbitals of equal energy, electrons fill them singly first with parallel spins. So all the spins will be up. Then when you come back, spins will be down. That's Hund's rule. Here's another mnemonic. I always screw up the drawing, so it's hard to, but it's like first shell, second shell, third shell, fourth shell, fifth shell, and so on. And then if you do this thing like this, watch the magic. You're going to do the 4s for the 3d. I have a hard time reproducing this, especially if you have a periodic table in front of you. So how do we write electron configurations? Lower energy orbitals fill before higher energy orbitals. Orbitals can hold no more than 2 electrons. Mentioned that already. When 2 electrons occupy the same orbital, they must have opposing spins. This is known as the Pauli Exclusion principle. When orbitals of identical energy are available, all of these are first filled singly by electrons with parallel spin rather than electrons in pairs. This is known as Hund's rule. Hund's rule and the Pauli Exclusion principle. Easy to confuse oneself, maybe. All right, so we've done hydrogen, helium, lithium. We're going to skip beryllium, I guess. We did carbon. So here's nitrogen. You look up at the periodic table, see atomic number 7. That means I've got to accommodate 7 electrons. Where are all the 7 electrons? So I tell students, just fill up the first row of the periodic table, drop down to the second row. That S block has 2 columns, accommodating 2 electrons. The P block has 6 columns because there's 3 orbitals, or a set of 3. All right, so 3 electrons in the p orbital. They're put in with parallel spin before I double up. So change when we go from nitrogen to oxygen, we got 1 more electron. So now we start to spin pair them up. And here's fluorine. And when we finally get to neon, we have a completely filled orbital set. So the noble gases used to be called the inert gases. Why do you think they're so inert? Yeah, they're happy. Everything is filled. Yeah, so a lot of chemistry is when, you'll get more for your money today. Here's some a chapter 10. Oxygen is missing 2 holes, and so it can accommodate 2 more electrons. That really explains why oxygen likes to form 2 bonds. Ammonia looks like that. Here we got H2O. Here we got NH3. Why does nitrogen like to form 3 bonds? Well, it can accommodate 3 electrons. Of course, carbon, previous slide, it likes to bond 4 times. So I've told you before, chemists are lazy. And if we want to know the electron configuration of something, we can use a shortcut. And it's called the noble gas core notation. When writing electron configurations for elements beyond neon or beyond any other noble gas, the electron configuration of the previous noble gas can be abbreviated by the symbol for the noble gas in brackets. So if I look at this, here's a nice completely filled orbital, set of orbitals. I got first energy level, the second energy level, and then the third there. And if I look at this and say what has 2, 4, 10 electrons, that'd be neon. So when I put neon in brackets, that represents that whole mess there. And we can quickly look at a sodium's electron configuration. It says that's got 1 valence electron. Probably makes this cation. What is the electron configuration for magnesium? Feeling lazy? Put neon down. 3s. See on the table there, 3s. Sodium, magnesium. What do I want to put here? Yeah, 2. When those 2 electrons go away, I get this. All right, so for fun, let's do chlorine. Let's do the electron configuration for chlorine. Well, let's not do chlorine. I'm trying to go somewhere. Let's do oxygen. All right, well, first row of the periodic table. Second row. All right, I see boron, carbon, nitrogen, oxygen. I'm gonna put a 4 in there. I just visually did that. And what should these numbers all sum up to? 8. And what atomic number do I see for oxygen? 8. So there's where all 8 of the electrons are. Now let's just do, what does oxygen like to form when it forms an anion? Has a name, oxide, right? Where am I going to put those electrons? I'm going to put them in this orbital here. So now how many's there? 6. So I tell students, everything wants to obtain a noble gas configuration. Metals do it by giving up valence electrons and forming cations. And now we say these are all isoelectronic with neon. Here, oxygen is isoelectronic with neon now. So these 4 chemical species all have the same electron configuration. I got 2 cations, an anion, and an atom that all have the same electron configuration. I think there might be some questions like that on Alex. There might be one like that on your take-home quiz. I'm told repetition is good. How do we distinguish between valence electrons and core electrons? Valence electrons are the electrons in the outermost principal shell, or I said they were in an outermost energy level. The principal shell with the highest principal quantum number. These electrons are important because they are involved in chemical bonding or the formation of ions. Electrons that are not in the outermost principal shell are called core electrons. Let's do the electron configuration for silicon. First row of the periodic table. Drop down. There's lithium, beryllium. Now we're cruising across. Boron, carbon, nitrogen, oxygen, fluorine, neon. Oh, drop down, and now we got sodium, magnesium, and silicon is right next to aluminum. 2 into that P block. I got this thing written. I see these 3s here. That's the highest shell. And I see 2 4 electrons in there. So that tells me silicon has 4 valence electrons and 10 core electrons. And of course, if I do carbon, 1s, 2s. Oh, I'm really having trouble. Wanted to make that line up. Carbon only has 2 core electrons, but carbon and silicon are in the same column because they behave similarly. We learned that was the beauty of the periodic table, and they behave similarly because they have the same number of valence electrons. So selenium, 6 valence electrons. There they are, 28 core electrons. So you'll see all the noble gases have a complete orbital set. That's why they're so unreactive. And you can see all these are 1 shy of a full orbital being filled up. That's why they take on 1 more electron, and you get fluoride, -1 charge, chloride, oxide, -2, sulfide, -2, phosphide, -3, and so on. All these back up to this noble gas, +1 for a lithium cation. Similar electron configurations, similar chemistry, same thing going on here. I'm supposed to finish this lecture today. So that's how we predict these charges. I wanted to just get to these last 2 slides, predictions and trends. We're going to look at 2 of them, size, and just look at size. This one's fairly intuitive. Size increases as you go down a column. So of course, neon's larger than helium. Oxygen is smaller than sulfur. Silicon's larger than carbon. This typically makes sense. What doesn't make quite as much sense is things getting smaller as we go across a period. And that has to do with we're adding more and more protons to the nucleus. And that increased charge sucks down the electrons. At least that's how I picture it. Even though we're packing in more electrons, we also have more protons, and that electrostatic atomic charge shrinks these down. So a neon atom is a lot smaller than a lithium atom. Ionization energy is the energy required to remove an electron, and it decreases as you move down a column in the periodic table, and it increases as you move to the right across the period. So going down, those electrons are farther and farther away. They're easier to pull away, so we say ionization energy decreases. As we're packing in more protons, we increase the charge and it shrinks down the size. So the negative electron's closer to the positive charge, it's harder to pull away. So maybe when we meet on Monday, I'll draw these. I like the trend arrows to point to the same direction. So this has the highest ionization energy, and it's the least metallic element. Francesium has the lowest ionization energy and is the most metallic element.